I'd like to thank the organization for giving me the opportunity to share my work with you today. I'm going to tell you a story today that shows that dopamine neurons are encoding rich information that a large body of research in dopamine and reward processing wasn't suggested before. This reward processing system has been having a lot of attention because essentially, if you can predict rewards, then you can behave adaptively. So the idea is that if you can predict reward, then you can select the actions that maximize this rewards for any given context in the environment, here state. And this is a principle underlying reinforcement models. And this allows for giving a logic for how animals learn behavior programs through interactions with the environment. So a big set of these models estimates something called value that we will represent here with a V. Value is the expected sum of cumulative rewards and can be learned using a temporal difference learning algorithm where at each time step it is updated by the reward prediction error and weighted by the learning rate, this alpha. The reward prediction error is a surprise signal. It tells you how good are you at predicting rewards in the environment. And it's equal to the immediate rewards plus the temporally discounted value at the next time step minus your current estimate of value. Importantly, this parameter that we represent as a gamma, the temporal discount factor, measures how much future rewards is devalued relative to immediate one. So in the case where an auditory cue predicts water, initially our value is flat and equal to 0 because we don't know that it predicts water. Then once we experience water, this value is increased at the time of reward delivery. And then through experience, this value is backpropagated until the cue. Here we consider a temporal discount equal to 1. So in practice, we're not devaluing the delay to rewards. But if we consider a smaller temporal discount, then the value backpropagated at the cue is smaller than the value at the reward. In the brain, it is thought that the basal ganglia are implementing a similar idea, similar algorithm, sorry. And the idea is that cortex provides information to the striatum about the state of the world, here time. The striatum is estimating the corresponding value using the reward prediction error signaled by these midbrain dopamine neurons. It was originally proposed that all dopamine neurons are encoding a unitary reward prediction error relative to an average expectation of future rewards. So they don't carry information about reward magnitude variability, for example. And this seems important for behavior. Sometimes maybe you might prefer certain rewards, and in other contexts, maybe you want to take the risk and go for a variable reward option. And this is a field in behavior economics. It's called risk attitudes. So here I give two probability distributions in green and in yellow that have the same average, and therefore standard temporal difference learning algorithms can distinguish between two cues that predict rewards sampled from these two distributions because they have the same average. So the way to solve this problem was proposed in the machine learning field through a set of algorithms called distributional reinforcement learning algorithms. In these algorithms, instead of estimating one single value, a set of values are learned that differ in their level of optimism. So what do I mean by optimism? So here is a plot of the reward prediction error as a function of reward magnitude for the tuning of these different units. You can see that the tuning of these units are asymmetric linear functions that have a zero crossing. This zero crossing is called the reversal point, and essentially is the reward amount that each neuron is expecting, because they had a zero reward prediction error. In particular, we call this blue neuron here a pessimistic value because it converges to a negatively biased estimate of value by giving a bigger weight to negative compared to positive reward prediction errors. And this one neuron here in red we call optimistic because by giving more weights to positive than to negative reward prediction errors, it's pushed to the high end of the reward magnitude axis and converges to a positively biased estimate of value. It has been shown that midbrain dopamine neurons in mice implement a similar algorithm. And importantly, by knowing the variability in these reversal points and the asymmetry for the positive and for the negative reward prediction errors, this allows for decoding at the reward time the probability distribution over reward magnitudes. So here is in gray the distribution they gave in the experiment, and in blue is the decoded distribution from the population of midbrain dopamine neurons. So this code allows for distinguish between the variable and the certain Q I described to you before. However, value also doesn't carry information about when the reward will happen. If now we add another Q, a purple Q, that predicts a larger later reward, then the value at the Q of these three Qs is the same. If we plot the value at the Q as a function of reward magnitude and time, we see that there are many combinations of reward times and magnitudes that have the same color, the same value. So value can disambiguate between the reward time and the reward magnitude. So to solve this problem, we reasoned that maybe we could generalize the distributional magnitude reinforcement learning idea to the time domain. And this is the principle of our work. So we generalize the distributional RL in magnitude to time, and then try to combine the distributional in time and magnitude. So this could be implemented by considering a set of values, optimistic values, by considering a set of neurons that would discount the delay to reward in different ways. So the idea is very similar. So if we plot the responses at the Q as a function of reward time, each curve here is a neuron color-coded by the temporal discount. And if you look at the population snippet at the onset of the Q, then you can see that the population response's shape is very different for the early compared to the later reward. And this is what allows to, in principle, decoding at the onset of the episode, the probability distribution over reward times. So then we thought that by combining the distributional, this hypothesis with the distributional code in magnitude, we could predict at the reward time, at the Q, how much the reward will be and when will it happen. So we propose a distributional reinforcement learning that is in time and magnitude that we call TMRL. So in this case, the neurons are tuned to reward time, implemented with a temporal discount function, and have also a level of optimism implementing by these asymmetries for positive and negative reward prediction errors. And this allows for decoding at the Q the joint probability distribution over time and amount. So this is a map of future rewards in the environment. And it can distinguish between the toy example I've been showing you throughout this presentation. So if you look at the magnitude axis, it can distinguish between the variable and the certain Q. And if you look at the time axis, you can see that it distinguishes clearly between the early Qs and the later Qs. So we wanted to understand if the brain is implementing a similar algorithm. So we designed a behavior task and looked into dopamine neurons that are thought to encode these reward prediction error signals. So we wanted to test if this population show diversity in temporal discounting. If this diversity in temporal discounting carried information about the reward timing, and that by combining the previously proposed distributional code in magnitude with this code in time, we could extract information about the joint probability distribution over reward time and magnitude. So before I delve into data, I want to say that all the data I'll present here today was collected by Bruno Cruz, a former PhD in the lab, and Pavel Podjalski, a current postdoc in the lab. So we designed a classical conditioning task where one Q predicts a variable reward magnitude sampled from a bimodal distribution, so the endpoint amounts are more probable of happening. And with this Q, we estimated the value each neuron is expected. So here's a raster for a single neuron aligned to the reward delivery. We can see that the bigger the reward amount, the more this neuron fires. We can look at the temporal profile for each of these conditions and compute the responses for the different magnitudes. And with these responses, we can estimate the value this neuron is expected. Here, in this case, it's 5.37 microliters of water, and estimate the slopes for the positive and negative reward prediction errors. We call this neuron an optimistic neuron because it expects more than the average of the distribution that we give in our experiment. And if we do this for all the dopamine neurons we recorded from, we are able to decode at reward time the probability distribution over magnitudes. And this had been already shown. But we also wanted to understand if there were variability in the temporal discounting in this population of neurons. So we added 4 extra cues that predict a certain reward amount after different delays. First, I'll just show you that it seems that animals can distinguish between the 4 cues. So this is the lick rate as a function of the time since Q. We can see that in the beginning of the trials, the slope in the lick rate is very different for different cues. And with these cues, we estimate the temporal discount of each neuron. So here's a raster aligned to the cue delivery, sorted by reward delay. We can see that the longer the reward takes to come, the less this neuron fires. We can look at the temporal profile for these different conditions, compute the responses, and with these responses, we estimate the temporal discount. And we can do this for all the neurons we recorded from. You can see that this neuron here on the left discounts more the delay to reward than this neuron on the right. So we call the neuron on the left an impatient neuron. He wants faster rewards than the neuron on the right that we call patient. So we can do this for all the neurons in the population. This is the firing rate at the Q for different reward times. Each dot here is the mean firing rate for a single neuron. The curves are the fitted temporal discount functions. In blue, we have the mean population temporal discounting function. And we can see that indeed, it seems that this population reveals heterogeneity in the temporal discounting of rewards. But we wanted to understand if this diversity, and one of the things we wanted to test was to see if this diversity contained information about the reward timing. So we took the firing rates at the Q of the population and decoded the probability distribution over reward times. And we can see that the decoded densities can capture the differences in the timing of these different Qs. So the system has available at the Q information about when the reward will come. So then this begs the questions, are animals using this information to guide behavior? If they were using this information to guide behavior, then when they behave as if they expect the reward to come earlier, then the density we're decoding from this population of neurons should be shifted towards earlier reward times. So we divide trials in which the animals start licking earlier or later, and decode the density from these set of trials. And we can see that when the animals started licking earlier, this density is shifted to the left, to earlier reward times, compared to when they started licking later, that's shifted to the right, to later reward times. And this seems qualitatively consistent across all reward times. So it seems that these neurons have access to the same information used by animals to guide when to start licking. And importantly, this information was decoded at the cue, at the onset of the episode. And it's used in that current episode to drive behavior. However, in the previous distributional code in magnitude, this information was only shown to be present at the time of rewards, at the end of the episode. And this doesn't seem very useful to drive behavior in that current episode. But in theory, this information should be backpropagated from the reward until the cue. But if we look at the reversal points, that are the values each neuron is expecting that we measured at reward time, we can see that there's no clear relationship between these values and the firing rate at the cue. But remember that I've just shown you that it seems that these neurons discount in a diverse way the delay to reward. So now if we take into account this diversity, we see a clear relationship between the values they're expecting and the firing rate at the cue. And this allows to decode at the cue the probability distribution over reward magnitudes. So in summary, I've shown you that the population of dopamine neurons seems to heterogeneously discount the delay to rewards, and that this contains information about when the reward will come, that the decoded reward time, that the reward time prediction derived from this population of neurons is correlated with anticipatory behavior, and that by having knowledge of that diversity in value and in temporal discounts allows for decoding at the cue the probability distribution over reward magnitudes. So we have separately decoded the distribution over magnitudes and times. But we wanted to understand if we could jointly decode the probability distribution over reward times and magnitudes. So we took the population responses for each cue and decoded this two-dimensional map of rewards in time and magnitudes. So this is the decoded density for the cue predicting after 3 seconds a certain reward amount of 4.5 microliters of water. And we can see that there's a clear one single blob. But then we wanted to understand, can we see the two blobs in the case of the cue predicting at the same time a variable reward magnitude? And we do indeed see the two blobs. And looking here at the magnitude axis, we can see that the decoded density clearly captures this variability in reward magnitudes. And this seems true for all the cues in our experiment. I want to pause here for a second. So this very rich map of the future rewards in the environment was constructed using the mean activity of only 43 dopamine neurons in a very short window of time for 150 milliseconds. And it allows for this very rich representation of rewards in the environment. It allows for basically a model of the rewards in the environment. But I've shown you during this presentation that it seems that the mechanism to learn this rich information is very simple. It's the local temporal difference learning algorithm, but with a tweak, considering a diverse set of temporal discounts and asymmetries for positive and negative reward prediction errors. So then, we indeed saw that by combining this distributional code in time and magnitude, we could decode this two-dimensional distribution over times and magnitudes. But then we wanted to understand if this variability that we're measuring in these neurons tuned to reward times and magnitudes is something that we as experimenters are exploiting, or is it something that the system is regulating in order to maximize information about these dimensions? So the system has available a constrained number of neurons. And if the system wants to maximize information about reward times, then if the reward times in the environment only occur at short reward times, then it shouldn't waste coding capacities in longer reward times. So the tuning functions of the neurons should shift to the left. So the temporal discount should decrease. On the other hand, if the distributions given in the environment are biased to longer reward times, then the tuning of the neurons should shift to the right to more accurately encode these reward times. So the temporal discount should increase. And this is a principle of efficient coding. So to test this idea, in the end of each recording session, we manipulated the reward time statistics by taking either the shortest or the longest delay. And we measured the temporal discount before and after we did this manipulation. So each dot here is a single neuron, and this is a temporal discount before or after we either took the shortest or the longest delay. And we can see that the mean adaptation in the population when taking the longest delay so the temporal discounts decrease than comparing when taking the shortest delay. So it seems that the system is indeed regulating and adapting the tuning functions of these neurons in order to maximize information about the reward times in the environment. And we can do a similar analysis for the reward magnitude axis. So this is a similar idea. If the system only has available a constrained number of neurons, then to encode the variable Q, then the range in these values should be bigger than to encode the certain Q, where the values should be all close together. And we measured the variability in the variance in the reversal points for the variable Q and for the certain Q. So in the vertical axis, we have the variance for the points for the variable Q, and then horizontal for the certain Q. And we see that the variance for the variable Q is significantly higher than the variance for the certain Q. So it seems that the system is also adapting in order to maximize reward information about this new feature of rewards, that is magnitudes. So it does seem that these neurons are adapting to changes in the statistics of rewards, and this is a strong evidence that is telling us that the system is indeed targeting these dimensions in order to maximize the information that it encodes about the reward times and magnitudes. So the big picture implications of our work is, so now we're trying to understand how we can use this very rich information that is available at the Q to drive behavior programs. And we think this can be useful when the reward is dynamic. So when the reward is dynamic in very constrained intervals of time. And we think this is an interesting example of efficient coding in the reward system, because previously efficient coding has been shown to be present, but more on the sensory systems. And on the other hand, we think that this efficient coding idea applied to rewards can be a normative framework to understand psychological characteristics such as impatience and optimism. And so the idea is that maybe someone is impatient because the brain is somehow adapting its temporal discounts to maximize information about the reward time she experienced in the environment. So maybe if the environment is very volatile and rewards only happen for sure in short reward times, and this can be a consequence of this adaptation in this code. So I want to thank my lab for all these years and everyone involved in this project. So Pavel Podjalski, Bruno Cruz, Kenry Louis from NYU, Daniel McNamee, and Joe Patton. and you for listening to me today.